afternoon, everybody. First of all, I would like to thank CEFIPRA for acceding to our request and allowing us to have this workshop, through which we hope that we have a good interaction between Indian and French academia and industry. I would personally also like to thank Professor Jean-Christophe Nalatambi, who actually was instrumental in getting this workshop, for the realization of this workshop. Now, I have a very difficult task because my talk is just after lunch and I must keep you from falling asleep, right. So, I hope I will be able to do that. Let us see, because what I am going to do is just to give you an overview of the kind of research we are doing in gallium nitride technology development at IIT Madras. We call it our grand journey. GRAND stands for Gallium Nitride Research and Development. So, our grand journey actually started more than 10 years ago, as you can see, in 2012. At that time, around that time, there were quite a few institutes in India who were growing gallium nitride. Our mandate was to estimate the quality of those wafers, and we started our research work by fabricating LEDs. That was in 2012, and you can see some of the pictures. That was LED emitting at 410 nanometer and so on. So, the wafers were grown elsewhere in India, and then we fabricated the devices. After that, from 2014 onwards, we have been working on HEMTs and graduated to Miss HEMTs and finally to Miss Fin HEMTs. As you can see, I have traced here generation 1, which was pretty big device with gate length of 4 micrometer. Went to Gen 2, gate length was reduced to 1.5 micrometer. In Gen 3, the gate length was reduced to submicron level, and now actually we are working on in the last 5 years or so, we have been working on Gen 4 and Gen 5, where the gate lengths are of the order of 225 to 250 nanometer, and we are working on HEMT, Miss HEMT, Fin HEMT and Fin Miss HEMTs. And of course, all these things would not have been possible without a lot of support from, we have a lot of support from DST, DRDO, SERB, MEITI and of course, IIT Madras. I am very glad to see Dr. Raul here, because our gallium nitride research work actually started with a lot of help from SSPL, which is under DRDO. Now, I would just like to tell you what are the salient points of our technology development in gallium nitride. As you know, in India and all over the world, gallium nitride is a very hot topic and so many people are working on that. So, what is special about our research? Well, the first point is that our devices, mostly we are focusing on aluminum indium nitride on gallium nitride, not on the conventional aluminum gallium nitride substrate. I will tell you the reason why. We have done work on aluminum gallium nitride also, but our main focus is on aluminum indium nitride on gallium nitride. Secondly, currently our focus is mostly on Miss HEMT and Miss Fin HEMT. Miss stands for metal insulator semiconductor. So, these are not Schottky gated HEMTs, these have a thin dielectric layer introduced between the gate metal and the barrier. And finally, our focus is on realizing enhancement mode devices. Enhancement mode devices means devices which are normally off, that means they should have a positive threshold voltage. And of course, in gallium nitride, one problem, if you can call it a problem, is that mostly all devices are depletion mode, that is they are all normally on. So, you need to apply a negative voltage to the gate to make it off. Okay. Now, by contrast, if we can have a normally off gallium nitride based HEMTs, then of course, it will be a much more energy efficient process, it will be fail safe, and of course, it is preferred. but so many people are trying different ways to realize these enhancement mode devices, but till today all gallium nitride based power amplifiers are designed with depletion mode HEMTs, though a lot of research is going on all over the world in order to fabricate reliable enhancement mode GaN HEMTs. I will tell you how we are approaching it. Different people are approaching it in different ways. I will tell you how we are approaching this. So, let me first start with why we focused on aluminum indium nitride. Now, when I say aluminum indium nitride, I mean a particular composition of aluminum indium nitride, which has 0.83 mole fraction of aluminum, 0.17 of indium and nitrogen. Okay. Now, here you see this particular composition of aluminum indium nitride is lattice matched to gallium nitride. As you know, one problem in the AlGaN-GaN heterojunction is that aluminum gallium nitride is not lattice matched to gallium nitride. As a result, there is a lot of inbuilt strain in the aluminum gallium nitride layer, and these are all piezoelectric materials. So, when we apply voltage during operation, there is going to be further stress developed in the barrier material, which leads to a lot of defect generation and eventual malfunctioning of the device. So, in order to make these devices reliable, we felt that aluminum indium nitride will be better suited because it is lattice matched to gallium nitride when we have a mole fraction of aluminum of 83%. Now, because it is lattice matched, obviously the strain dependent polarization, which we call the piezoelectric polarization, that component will be absent in aluminum indium nitride layer. However, even though the piezo polarization is absent in aluminum indium nitride, we have a much higher spontaneous polarization in the barrier layer, and therefore, the two-dimensional electron gas density is much higher in aluminum indium nitride gallium nitride system compared to aluminum gallium nitride system. So, we have so these are basically the two advantages of aluminum indium nitride, and it allows us to go for much thinner barrier layer, and therefore, we can actually get much higher transconductance also. So, we can have much higher current drive, much higher transconductance compared to aluminum gallium nitride heterostructure. However, let me now tell you why we chose to go for mis-HEMTs to begin with. As we know, HEMT devices, they use a Schottky gate at the on the channel, and Schottky barrier gate obviously means that there will be higher gate leakage, there will be limited positive gate voltage swing, of power dissipation will be much higher, and all these problems are much more aggravated when we go for aluminum indium nitride gallium nitride. So, I was telling you about the nice things about the aluminum indium nitride gallium nitride system, but there are lots of negatives as well. And these issues, as I said, particularly the limited positive gate voltage swing and high gate leakage, these are much more severe in aluminum indium nitride and aluminum nitride. And this comes from the inherent fact that in aluminum indium nitride gallium nitride system, we have a much higher spontaneous polarization, and that means that the electric field in the barrier is much higher compared to the aluminum gallium nitride system. Now, because this electric field is much higher, on one hand it is good because it allows us to go for a thinner barrier layer, and therefore, we can have high transconductance. But the other problem is that because this electric field is so high, the leakage, the gate leakage is also very high, because you see mostly the gate leakage mechanisms in a Schottky gate will depend on the electric field, whether we are talking about Pull-Frankel or the Fowler-Nordheim tunneling, they will all depend on the electric field, and because this electric field is so high, you will see that in aluminum indium nitride gallium nitride heterojunction we get right. So, just to bolster what I said, I have here two sets of experimental data. One, the top one is for aluminum gallium nitride HEMT, and the bottom one is from the aluminum indium nitride gallium nitride HEMT. And what is the first thing you notice? You notice that the gate leakage current is about 1 order of magnitude higher, more than 1 order of magnitude higher for aluminum indium nitride gallium nitride, and this is because the electric field is so much higher. Not only that, if you also look carefully, you will find that in case of aluminum gallium nitride HEMT, the leakage current is dominated by Poole-Frankel mechanism. PF stands for Poole-Frankel. Whereas, if you look at aluminum indium nitride gallium nitride HEMT, you will find that beyond a certain gate voltage, it is also dominated by Fowler-Nordheim tunneling. So, all these leakage current components add up, and therefore, we have a very high leakage current in case of aluminum indium nitride. So, as I said, we have higher polarization charge and therefore higher electric field, which is good in a sense, but which is bad because the leakage current is also going to be much higher due to this high electric field. So, obviously then if we are going to work on aluminum indium nitride gallium nitride heterojunction, then we need to work on MIS HEMTs, where we will introduce a thin gate dielectric between the gate and the barrier in order to reduce the gate leakage current. And well, this is the figure, this is the process steps for submicron gate length MIS HEMTs with e-beam lithography. So, I have started with the substrate where the source and drain has already been fabricated. So, as you can see here, we have the aluminum indium nitride barrier layer and the source and drain contacts are already given, and on top of that now we are doing the e-beam lithography. So, we are using PMMA A8 e-beam resist and directly writing the gate pattern in e-beam lithography with 30 kilovolt source, and these are for gate lengths of approximately 250 nanometer. And here we have used PECVD silicon nitride, about 7 nanometer of PECVD silicon nitride as gate dielectric, and the gate metal is nickel gold, and after the standard lift off process, you can see here the gate is sitting on this very thin silicon nitride layer, and finally we have the actual device. So, this is the MIS HEMT fabrication, where the gate dielectric is silicon nitride. We have also fabricated MIS fin HEMT. In fin HEMT, the advantage is that the gate from all 3 sides are going to control the channel, and so essentially, I mean, if I can just use an analogy, if I can say that this is my MIS HEMT, let us say this is the channel, and on top of the channel I have the gate dielectric, and on top of that the gate method is coming. When I talk about fin HEMT, it is actually like this, and the gate is draped over the structure. So, that means I have the gate covering the channel from all 3 sides, the 2 side walls as well as from the top. Obviously, then in a fin HEMT, the control of gate over the channel is going to be much better, and we saw that when we fabricated both MIS HEMT and MIS fin HEMT with same or similar gate length, we found that the MIS HEMTs show a lot of short channel effects, whereas a MIS fin HEMT shows almost an ideal IV characteristics. So, this is the MIS fin HEMT fabrication with submicron gate length. As you can see here, the region between the source and drain, we have the fins, multiple fins, and that fin is written by EBL. And you can see here the SEM picture, it is about of the order of 200 to 225 nanometer fin width. Now, this is a comparison of MIS HEMT and MIS fin HEMT The IV characteristics I am showing here is only of Miss Finhemd. As you can see, the characteristics looks pretty decent, it looks like almost ideal characteristics. If you look at ion by I of ratio, even that is much better for Miss Finhemd. Obviously, the GM is much better for Finhemd, it is 327 for Miss Finhemd and 285 for Miss Hemd. Not only that, the GM is much flatter for Miss Finhemd compared to the Miss Hemd. The only point is that of course, the FT for Miss Finhemd is not as good as that of Miss Hemd, and that is because while the sidewalls have advantage of, that is the side gates, they give you a better GM, they also add to the capacitance, and because of this additional capacitance we have much comparatively lower FT than the Miss Hemd. Okay. I will now come and talk about the enhancement mode device. This is the technology development that I talked to you about. This is about the Miss Hemd fabrication and Miss Finhemd fabrication. Now, let us look at the enhancement mode device and how one can achieve enhancement mode devices in using this gallium nitride platform. Now, as I keep saying, there is in the Finhemd or Miss Hemd, we have the side gates as well as the top gate, and these side gates can also deplete the channel charge. Therefore, in Finhemds there is always a shift in the threshold voltage which makes the threshold voltage less negative. So, we try to use this property of Finhemd in order to realize an enhancement mode device, and the amount of the shift in the threshold voltage will depend on the fin geometry. So, we try to tweak the fin geometry and see how the threshold voltage is going to change. Another approach towards enhancement mode device is by charge engineering. We all know from our knowledge of MOS technology, MOSFET, that is, if there are charges present in the gate dielectric or more pertinently at the interface of the gate and the channel, then it can shift the threshold voltage. If we have positive charges in the gate dielectric, it will make the threshold voltage more negative. If we have negative charges, it will shift it to the positive direction. So, we have actually tried to use that charge engineering in order to shift the threshold voltage towards the positive direction. If I can just go back for a moment, I wanted to tell you something. When I was comparing the Miss Hemd and Miss Finhemd, as you can see here, the gate length of both of them is about the same, 225 nanometer, 220 nanometer. But just look at the threshold voltage, you find that while for Miss Hemd the threshold voltage is minus 4.6 volt, for the Miss Finhemd it is actually shifted more towards the positive direction and it has got shifted to minus 1.5 volt. So, as I told you, the modulation in the threshold voltage is going to depend on the Finhemd geometry. So, this is what we have made use of, and now look at the enhancement mode Finhemd that we have made. Here actually the fin width is reduced to 80 nanometer. The previous one, the fin width was about 100 nanometer. The length, gate length is 350 nanometer, and here if you notice, you find that the threshold voltage has now got shifted to plus 0.63 volt. So, it is actually a normally off device. So, it is possible to realize an enhancement mode Finhemd by doing the by tweaking the geometry and going to a narrower fin width. So, this was one approach, this is one approach. We have been able to demonstrate the enhancement mode type device. However, we still need to do a lot more work in order to standardize this process and to improve the yield of the process. Now, another approach that we have used is I said the charge engineering. Sorry, yeah. So, as I said, we have also tried to do charge engineering in gate dielectric, and for this the gate dielectric that we have used is aluminum oxide. Now, I already mentioned that shift in the threshold voltage could be due to charges in the gate oxide. There can be a negative shift if you have positive charges in the gate oxide. By the same logic, then it is possible to have negative charges at the interface, and it can lead to positive shift in the threshold voltage. Now, when we do a composition analysis, we find that usually people have reported a negative shift in the threshold voltage for MESEMT, and that is because of the oxygen vacancies at the interface. That is, at the interface the aluminum oxide is not really Al2O3, it has oxygen vacancies. It has oxygen vacancies, and therefore, it is aluminum rich aluminum oxide, and that gives rise to a lot of positive charges. However, if you can have a process in which you are having an oxygen rich aluminum oxide, then it is possible that you can have more negative charges introduced at the interface, and therefore, the shift in the threshold voltage can be positive. So, this is what we tried, and we were successful to some extent. So, this is an energy band diagram of the system we have. We have an aluminum indium nitride gallium nitride heterostructure with a thin gallium nitride cap, an oxide and a metal. And if you look at this, then you find that one possibility is that we can go for a thicker oxide. Okay. So, you see, this is the threshold voltage of the HEMT. If we have more negative charges at the oxide gallium nitride interface, then of course, the threshold voltage is going to reduce, and we are going to have a less negative threshold voltage for the MESEMT. And if we can make that oxide thicker, then of course, as you can see here, look at the electric field distribution in the oxide. This is how the energy band is going to bend, and then we are actually going to have a change of sign in the threshold voltage, and if you can use a thicker oxide, then the threshold voltage can actually be positive. This was a hypothesis, right? I will show you that this hypothesis was not 100% correct, but at least here it looks as if we can make the oxide thicker, then it is possible to go for it is possible to achieve a positive threshold voltage, provided the charge in the oxide or charge at the oxide semiconductor interface is all negative charges. The other possibility is of course to go for a thinner barrier. Again the same thing, if you have a thinner barrier, then you can see here this is the same HEMT threshold voltage of the HEMT, but look at the thinner barrier, and if you have a thinner barrier, then of course you can see that the threshold voltage of the MESEMT is actually changing its sign and it is becoming more positive. Okay. So, we try to make HEMTs or MESEMTs rather with different gate dielectric thickness. As I said, our idea was that if we increase the gate oxide thickness, then we should be able to get a positive threshold voltage. At the same time, we also used a recessed gate aluminum indium nitride gallium nitride, because as I said, if you have a thinner barrier, then also you are supposed to get a positive threshold voltage. What we found is that the positive shift in the threshold voltage is much better, much higher for aluminum indium nitride gallium nitride MIS diodes compared to aluminum gallium nitride diodes. That means that aluminum indium nitride gallium nitride heterostructure is probably more suitable for making enhancement mode devices. And I have here the two sets of CV characteristics showing the threshold voltage. As you can see here, this is the CV characteristics of the Schottky barrier diode showing a large negative threshold voltage, and then as we keep on increasing the gate oxide thickness, you can see 5 nanometer to 8 nanometer to 13 nanometer, the threshold voltage is actually shifting more and more towards the positive direction. So, as I said, our hypothesis was that thicker gate oxide will make the positive shift more and more, was partly justified, because eventually when you go to a much thicker gate oxide, 23 nanometer thick oxide, we found that the threshold voltage is again starting to go back. We have a reason for that also, I will come to that later. Similarly, you can see here, this is the set D, that is the recessed gate oxide, and here also you can see from 6 nanometer to 11 nanometer to 19 nanometer it is increasing, but then when you go to 25 nanometer it actually goes back, the threshold voltage starts to go back to more negative direction. So, what do we see? We see that as we increase the gate oxide thickness, the threshold voltage becomes more and more positive, but beyond a certain point it starts to reduce again. So, we did a lot of experiment, and you can see these two comparison between aluminum gallium nitride heterojunction and aluminum indium nitride gallium nitride heterojunction. We find that the variation of the threshold voltage with TOX is not monotonic. Now, why is it not monotonic? That is because the composition of the aluminum oxide that we deposited is not really uniform. While close to the interface we did have oxygen rich aluminum oxide, beyond a certain point it started to become more aluminum rich. As a result, we had presence of both negative and positive fixed oxide charge. Now, interestingly, the point was that the negative fixed oxide charge was really located as a thin sheet of charge at the interface of the oxide and semiconductor, whereas the positive fixed oxide charge was distributed in the gate oxide. Therefore, what was happening is that beyond a certain thickness, it is the positive fixed oxide charge which started to dominate over the negative fixed oxide charge, and that is why you see that the threshold voltage reaches a peak positive value and then it starts to reduce again. So, as I said, we have done a compositional analysis also, and we looked at the distribution of the fixed oxide charge. As you can see here, when we plot the aluminum to oxygen ratio versus the thickness of the aluminum oxide, what we find is that at the interface it is more oxygen rich, but then as we are moving away from the interface it is becoming progressively aluminum rich with increasing TOX. So, we have negative oxide charge at or near the interface because of excess oxygen, whereas in the bulk of the aluminum oxide we have positive oxide charge, and that is what is giving rise to this non-monotonic nature of the threshold voltage variation. So, again here we were able to obtain enhancement mode aluminum indium nitride, gallium nitride miscemt, these are the characteristics. We were able to obtain a threshold voltage of plus 0.67 volt with very good ion by I of ratio. These are of course much larger device. Here the gate length is about 2 micrometer. And we did a lot of reliability study, because whenever we are depending on charge engineering on threshold voltage, the first question is how stable is this threshold voltage. So, we did a lot of stability analysis, and we found that both for temperature stress and for voltage stress, the variation in the threshold voltage, the change in the threshold voltage is within acceptable limit. So, the fabricated devices showed better threshold voltage stability than many other reported miscents. So, finally, to come to the summary of our work, our focus is towards realizing enhancement mode devices, and we have tried two approaches. One is that of fin miscemt and the other one is that of charge engineering. And these miscems that I showed you with aluminum oxide gate dielectric, here the aluminum oxide was deposited by reactive ion sputtering, and that showed positive shift in the threshold voltage, which is obviously exploited for E-mode MIS devices. And we have also done detailed analysis on why the shift in the threshold voltage is not monotonic, that is because of the presence of both negative and positive fixed oxide charges. And we have also proposed an analytical model which probably tomorrow Amita will present. So, using optimized barrier and oxide layer thickness, it is possible to demonstrate enhancement mode aluminum, indium nitride, gallium nitride devices. So, our vision is a long term goal. We want to create a gallium nitride research facility which is comparable to the best in the world doing cutting edge research, and we now have a gallium nitride research center, and we want to make it self sustainable with a large number of faculty and students, and the center most importantly which will work closely with industry to provide solutions and also provide trained manpower for the industry. These are the faculty members associated with our group, and all that I have presented here, these are all work done by our students. Okay, I am only presenting the work, work is actually done by the students. So, we have a lot of students past and present, some of them are already working in industry or in academia, and some of them are present here today, and they also have put up some posters. You can see those posters for more details of their work. Thank you very much for your attention.
So, I just wanted to know the fin hems you have fabricated, whether they are on they are algan GaN based or aluminum indium nitride GaN.
Mostly they are all aluminum indium nitride on gallium nitride, but we can also fabricate on aluminum gallium nitride.
So, the question is actually you said the aluminum indium nitride and GaN based they have almost negligible lattice mismatch. So, there isn't any strain, and when we do FinFET type of geometry of gate, and there is a strain relaxation, right. So, that is the reason of mainly the reason of threshold voltage shift is due to strain relaxation.
Not only, that is a model, yes, but we have also given a model. Amita will tell you about that model tomorrow. In aluminum gallium nitride fin hems, you see that the threshold voltage shift is people propose that it is due to strain relaxation, but we have found the threshold voltage shift even in aluminum indium nitride gallium nitride hems, and therefore the reason cannot be strain relaxation, right. We have shown in our model, which will be discussed tomorrow, why it happens. It is essentially because you see you have the two side gates, okay, and that these two side gates are also depleting the channel. It is basically a tri-gate structure.
Okay.
So, that is why primarily strain or no strain you will have a shift in the threshold voltage.
Okay, one more thing was you have fabricated the thicker oxide GaN hems. So, what is the application for using?
No, it was only a study, like I am telling you that from our analysis we thought that if it is because of the presence of the charges in the oxide, then as the oxide thickness grows, more and more charges will come into picture and it will shift the threshold voltage more towards the positive direction.
Just for analysis purpose.
But of course, the question is, I mean, you do not want to make a very thick gate dielectric because then your GM will fall. We just wanted to prove our hypothesis, and we saw that it is not 100% true. You can increase the threshold voltage up to a certain point, but beyond a certain point it will start reducing, because now the positive charges in the gate dielectric will come into picture. So, our optimized thickness was actually 7 nanometer.
Okay.
The negative charges, we found they are actually a thin sheet of charge. Okay, they are confined within a few nanometers. Okay. However, the positive charges, they were getting distributed in the gate dielectric, because I mean, it is because of the composition at the interface within a very thin layer. If I can just go back to that XPS analysis.
So, my question was in the energy space. So, these are mid-gap charges or these are mobile charges?
These are not mobile charges, these are fixed charges. These are fixed charges, these are because of oxygen interstitials. Okay, it's oxygen rich aluminum oxide. So, there are oxygen interstitials and that they are not able to move. So, it's fixed charge.
And how deep or shallow they are in the energy space?
We haven't really done that analysis to see where they are located. You mean where they are located, right? No, we haven't really done that. What we have modeled it as a thin sheet of charge, just as an interface charge. Okay. So, if you look at this, you will find that as the thickness of the aluminum oxide increases, you see how the composition changes. Okay. So, that is why the negative charges are located very close to the thickness to the interface. You see they are located within about 2 to 3 nanometer, you see that, and beyond that you find that the aluminum to oxygen ratio is actually increasing significantly.
So, I wanted to know about the current density comparison between a fin-hemmed and a normal mis-hemmed. So,
quite comparable. I mean, I thought I showed you one plot. Let us see. Yeah. So, if you look at this ID, you see it's here it's they are almost same dimensions as far as the gate length is concerned. So, you can see ID max is about 0.87 for mis-hemmed and slightly better.
on state when you have high V into I dissipation, so is the dissipation a function of the fin width, like self-heating effects?
In fin-hemmed, the self-heating effect is much less, as you can see from this plot. Look at this plot, the self-heating effect is actually much less.
Okay, but in mis-hemmed it would be more prominent.
Yes.
So, what would explain that difference in self-heating effects between fin-hemmed and a non-fin-hemmed structure?
I think it's because the heat gets dissipated easily for fin-hemmed.
I had a question regarding the deposition process of the gate dielectric.
For the deposition process of
Yeah. So you are using reactive ion sputtering for Al2O3.
For Al2O3.
Any
yes.
particular reason for that? We can also use ALD.
Well, point number 1, we didn't have ALD at that time. Okay. Point number 2, we found from literature that most people have reported that ALD deposited aluminum oxide, they have positive charges, and therefore, the shift in the threshold voltage is more towards negative. Okay, I am talking about the time around 2016 when we were working. Most of the literature report on ALD aluminum oxide was that the shift in the threshold voltage was towards the negative direction. By contrast, it is very interesting, this is all called serendipity. Many years ago, early work on silicon photovoltaic devices, they used RIS aluminum oxide and they reported presence of negative charges in the reactive ion sputtered aluminum oxide. So, we said okay, let us try and see whether we can get the same thing.
So in that process you can actually change the composition of oxygen that you use and change the
Yes.
composition of Al2O3.
Of course. So, that is our next goal, that change the composition of aluminum oxide and see what happens. Trapping effect. Oh yes, of course. I think we have some posters on the trapping effect, both modeling as well as from the reliability point of view. In fact, we have some research scholars here, maybe you would like to talk to them. Because I didn't have much time, I didn't put on these things, but we have done a lot of reliability studies and we have observed some kinks in the IV characteristics, and the kinks have been characterized by the presence of traps in the semiconductor.
Long live India and France friendship.